the questions that one has to consider are, what are the essential data structures? And it's important to differentiate between the state data, which is where you're actually doing the calculation, the metadata, which is the meta information about the variables and other things that you're doing calculations with, and scratch data, the data that does not persist between your different evolution steps that you can reuse in many different ways, and how you manage these different data structures that handle these different kinds of data. You should also straight up identify different ways in which the data structures are manipulated. For example, what are the solver operations you're likely to have, what kind of communication and memory access patterns they're likely to give rise to, the housekeeping tasks that you will have to do with your data, the way in which the same data will be moved around, the ways in which the data structures interact with each other, and what is the minimal amount of metadata that you need in order for these interactions to happen without loss of efficiency and accuracy of your calculation. Where are the data dependencies? What are the things that physics won't let you get away with in terms of the usage of data, etc. And then how do you want to arbitrate on the ownership of data by various different physical components, because certain kinds of data, such as density in your hydrodynamic calculations, is modified by almost all physics that you might incorporate into your calculation. So who should own the field variable density, and who should have the access to modify it at what level? So that kind of arbitration needs to be decided upon. And then you have to work on how should you scope your data, where should the data be visible without doing an explicit accessor function use, and where should the data actually not be, where should the data have only accessor access, and where should the data have accessor as well as mutable access. The way you start architecting your code is to identify units of computation that you can logically separate from one another, and you turn them into components of the code. You encode these various components of the code into a framework which is then integrated, and therefore you incorporate modularity into your framework. Then you separate what is exposed outside, and all of this is basically your object-oriented programming concepts in some sense, but it's useful to reiterate them, because even if you are doing your programming in a non-object-oriented language like Fortran, even though it tries to be, it isn't quite object-oriented, it is worthwhile imposing this discipline on top of your program, irrespective of the language of use. You should define the interfaces through which the modules can interact with each other, and then you have to devise the control flow, which is basically the driver of your application. Now, like I said, these are the principles of object-oriented programming, and these are good principles to start with, but in scientific codes, they don't always work out as easily. And sometimes the reason why that is you can have two completely logically separate units, for example, that you should be able to separate completely, but then they have lateral interactions with each other that you can't get around with, and that because physics wants it that way, and there is no getting around it. Or sometimes there are so many sort of interconnections between the two separate units that you end up moving a lot of data around, and that completely kills your computational efficiency. So you have to keep these things in mind as you're designing your code architecture. So I will work through the code architecture with the Flash example. And when we designed the infrastructure for Flash, the architecture for Flash, these are the requirements that we were working with. That the problems of interest were all going to have multiple scales, and therefore AMR was necessary. But we also wanted to support a uniform grid, because when you're trying to test complicated physics with the whole complexity of AMR, you don't know where is it that your problem's coming from. Whereas if you can actually test out your physics with just a uniform grid, that separates the complexity of your testing a little bit. So we wanted to have AMR and uniform grid, which you could pick between at configuration time so that you can run your test with uniform grid first before you turn on the full complexity of AMR. We needed to be able to input runtime parameters. We of course needed parallel I/O. We needed in support for multiple species to coexist in the simulation, because there are when you're doing supernovae and you have nucleosynthetic yield, you have multiple species that are moving around, and things like physical constants, etc. The physics that's needed for even the base calculations that Flash does, the type of physics that the code was designed for is shock hydrodynamics for sure, which is compressible gas dynamics, or magnetohydrodynamics. We needed nuclear networks because we are looking at nucleosynthetic yield, equation of states, and not just your simple equations of states, but variety of equations of states depending upon the kind of application you're working with. Of course, time stepping methods for time integration, and then we also needed support for being able to compute the Lagrangian characteristics associated with calculations that come in many flavors, so we needed Lagrangian particles as well. So we devised classes of units, and in Flash we call them units because bulk of the Flash implementation is Fortran, F90, F2003, whatever you want to call it, and then they had their data modules. And when we called our units modules, it just led to confusion in any dialogue we were having about the design principles. So we just started calling Flash computational units as units instead of modules, and the data modules then are separate from them. So we have infrastructure units, and those do all of the housekeeping, such as maintaining the discretized mesh, the I/O, the runtime parameter, etc., etc. The physics unit, which have physics-specific implementations, and there is some fudging between physics-specific implementations and infrastructure implementations, and I'll give a specific example of that when I'm outlining the architecture of one physics unit in there. Monitoring units are the ones that log the process of a simulation. So there is a log file unit where anywhere during the simulation you can ask for a message to be sent to the log file, and it is just accumulated that you get at the end. There are units that collect the performance statistics of the run and summarize it at the end. So after every Flash run, you do get a summary of the performance statistics all through the run. The driver unit implements time stepping and basically orchestrates the interactions between different various units, the order in which they should interact with one another, and also manages things like whether you're starting a run from scratch versus when you're starting from a restart, from a checkpoint. The simulation unit in Flash is the most specialized unit. This plays many different roles. One is it defines the application, which means that this is where you give your initial conditions. If you have any specific customized boundary conditions, this is where you put them in. When the configuration script starts to build an application, it first looks at the config file that is sitting in your setup directory, because that's where it starts to look for the physics or the infrastructure that it should assemble. But there is another role that this particular unit plays, which is non-obvious, and that is that any part of Flash's source tree that you don't want to use as it is given to you, all you need to do is take the same file name, have its custom implementation, and place it in your application definition setup directory. The way the inheritance in Flash works is this will overwrite anything that is existent anywhere in the Flash source tree, and you will get the customized version. Mind you, you do not have to remove the file where it is sitting originally anywhere in the source. Nothing. You do not have to touch the base source tree. All you do is you make a copy of the file from the source tree, or you make a completely new implementation, and you just place it in your setup file, and you get the customized version of that particular functionality. And this is actually what lets people get started and running with Flash very, very rapidly, is because then they can make use of much of what's built in, and just small portions that they need to customize for themselves, they can go with it. In Flash's architecture, a unit is the basic architecture unit also. Flash, when you build it, you do not get a big, large, monolithic executable which has every source file in it compiled. No, what happens is the relevant portions of the source tree are picked up and assembled for you, which is then compiled. So you only compile the parts of the code that you're actually using in your application. So you use different units are picked up for setups. Also, because Flash supports applications in many different regimes, what happens is you can have a solver that, for example, works in one regime for one particular equation in physics but does not work equally well in another regime, and you may want a different solver there. So there is a provision for multiple alternative implementations of the same capability to coexist that you can switch between at the time of configuration. Each of the units then publishes its API through which other units can interact with each other, and that's what allows you to have the same, as long as you provide an implementation that essentially implements the whole API, you can have all of these multiple alternative implementations coexist. Flash also provides a null implementation for every function in the API that you have defined. Therefore, even if you do a subset implementation of the API, you're okay, because then you just get the null implementation for the rest of them. If you don't need those particular interfaces, you're fine. You can just do a subset implementation and you're good. The units can have subunits, and there is a very good reason for it, which I will explain with an example later. And it's not just that not all units are included in an application. It is that even if you include a unit, there may be some subunits within that unit that may not be included in a particular application. Data management takes also several different flavors. We have defined constants for globally known quantities, and these just make sense to do it this way. For example, the main data structure that carries all of the field variables of the mesh, discretized mesh, is a single 5-dimensional array. And so 3 are the spatial dimensions. 1 is the variable dimension, and the final one is the block, because it's a block structured AMR. And this array is generated at configuration time, which means that different variables can have different indices into the array as they are built. A density can be the first index in one application, and it can be the 4th index in another application. So instead of having to have every application be aware of what these indices are, what the configuration step also does is it defines these constants, which are then indices into the data structure, and these are globally known. And there are many other such similar quantities that need to be just globally known, and they just get put into this file called flash.h, where they're all defined constants. Data, each item of data is specifically owned by a unit only, and only that unit has the right to decide who gets access to the data and who gets to modify. When the data is to be shared by one or more units, then there is an arbitration, and this is a design process where you decide where does it make more sense, which unit it makes more sense for it to own the data. And then within the unit also, there are different scopes for different groups of data. For example, there is a unit scope data module, which is globally accessible to every part of the unit, all of the functions within unit. As you go into the subunit, there is a data module that is accessible only to that subunit, but anything outside of that subunit doesn't have a direct access to it. It actually has to explicitly ask for it through accessor functions if it needs that bit of data. All of the other data modules follow the general Flash inheritance, and the Flash's inheritance rule is that the Flash's object-oriented framework is basically the Unix directory structure and the combination of the config script and the setup tool which implement the architecture. So the inheritance is a subdirectory inherits all of the functions that exist in the parent directory, but if there is a file with the same name in the subdirectory, that replaces the file in the parent directory. So it's a recursive replacement form of an inheritance, and in the data modules also that same inheritance applies, is that all of the data defined at the parent directory is visible to the child directory, but everything defined in the child directory is not visible to the parent directory. When you need to do the large-scale manipulation of the data that's residing in 2 or more units, then instead of actually doing the data copy, we configure, we make the runtime transfer control back and forth between units so that the access to the data is readily available without violating the encapsulation of the units. So this is what a unit hierarchy in Flash looks like. You start out, every unit starts with a capitalized name, and there is the definition of its API and the stub implementation of every single function in the API. And because then the stub implementations are inherited by all of the specific implementations for that functionality that you develop. This unit now has 2 subunits. There is the main and something. So every unit will have a unit main, and which is where the primary functionality of that unit is implemented. But if there is some subset of functionality that sometimes you want and sometimes you don't want, that goes into another subunit that can be turned off. And API implementation starts to happen here. Now, in unit main, for example, there are these 3 different alternative implementations that can exist. All the 3 of them have certain implementations that are common, and they reside at this level because then they're inherited by them. Now, what these 2 boxes tell you is that there are certain implementations that are common to implementation 2 and 3, but are unique to implementation 1. And therefore, the subdirectory structure is reflecting that the common implementations are sitting at this level, whereas the ones that are different, unique to every specific implementation, are sitting in these green boxes level. And all of this is actually the wrapper layer of Flash. This is none of the, in this part of the code, no solver is implemented. No actual computation is going on. All that these are doing is these are assembling the data, assembling all of the dependencies, putting everything together for the kernel to be able to operate. The kernels then sit at this level, and this is where Flash's architecture rules stop to act, because what that allows us to do is to bring in a third-party software without altering it in any way, and then just build this wrapper layer on top of it and integrate it with Flash. And here is an example of the grid unit, which is the most complex unit in Flash. So grid has main, which manages the discretized mesh, whether it is uniform grid or AMR with paramesh, or Chombo, which also exists under this now. So uniform grid has only 1 implementation, whereas paramesh had 2 implementations, the earlier version for backward compatibility, 2 and 4, and here there would have been another box for Chombo if I'd completed it. Within paramesh 4, there are 2 different implementations, so you can see that the directory hierarchy can get pretty deep. Now, onto the grid, onto the subunits. Grid particles, this is where in the architecture you start playing with a situation where you have a unit which is Lagrangian particles, which is where you want to do things like advance them in time, map them, etc., etc. But then it needs that in order to do some of these things, you need intimate knowledge of the grid. Like, for example, when your particle got displaced and moved to a different block that's on a different processor, the particles unit does not want to know where to send it, right? So there are companion functions that are implemented in this subunit that exists within grid called grid particles, and this is where all of the functionality that is needed to interact with the data structures that are owned by the grid exist here. Back and forth control transfer that allows this to operate seamlessly and still lets them maintain their encapsulation. And similarly, and that's just the example, so there is a, within a subunit, then there are 2 particular subunits. Now, the other important thing is, the reason why these exist as subunits is that if you have a simulation where you're not using particles, in that case, you do not include the subunit in that implementation. And so what will happen is only the null implementations will come in and none of this code will be brought in. And that allows for your application really to remain compact. Similarly, the boundary conditions have a separate subunit of their own. Grid solvers is where the fudging between the physics and mesh really comes into being, because as soon as you go away from an explicit solver for your physics, it almost always needs solvers that need much more intimate knowledge of the grid. For example, if you're doing self-gravity with either a multiple solver or a multi-grid solver, it really needs to have access to the grid metadata in order to work right. Also, the multi-grid solvers can be used for more than one particular physics. The same multi-grid solver that you can use for self-gravity, you can also use for pressure in an incompressible solve. So then what happens is when you come across such capabilities, they go and live under grid solvers where they have full access to the grid data structures, and there is just an interface for the physics to be able to access them. So it's not always true that the full numerics for a particular physics reside in that physics unit. It can happen that some part of the numeric resides under the grid and some part resides under the specific physics. There are instances where a function from one subunit is called in another subunit, in which case you can run into a problem that your code won't compile if you haven't included that subunit. So we have a provision for a local API where the null implementations for those functions reside. And so when the configuration is building, the inheritance works by going through the unit API first and then going into the local API and then parsing through the rest of the tree. Now, there was a question earlier on about why do we have this Makefile snippets instead of just having them included. And this is the reason, just for the ease of being able to read, because what happens is when the setup is building, say it encounters the hydro unit first, and that says I want grid main. So all of the Makefile snippets that are sitting in these levels will be picked up and become a part of a grid dependency structure in the Makefile. And then it can go on to do something completely different, say, for example, some source term. And then it'll get to the unit, which is particles, which will say, I have a dependency on grid particles. So the configuration will come back and it will start going through the Makefile sitting here. Now, if you did not separate them out based upon different units, what will happen is in your Makefile, they'll be scattered all over the place, and finding where your grid dependence functions are all over the place. So instead of that, what we have opted to do is, for within a within a unit, we keep track of all of these dependencies that are getting built, and for each unit then we create a general Makefile dot the specific unit, and those are the only ones that get included in the Makefile. It just makes for much easier to traverse the whole Makefile finally when it is built up. So I thought I'd walk through the challenges of a unit design, and I've picked up what has been the single most difficult unit to design in Flash. And every new user that comes in with every new application comes and tells us that this is a crappy design, we need to scrap it completely, we need to redo it, and no one can come up with an alternative that works a whole lot better. And that is the equation of state unit, because all of the physics units demand a great deal from this. There are times when equation of state is in most cases, a simple algebraic expression that you apply on each point completely individually of every other point, right? So there are times when you're given certain physical quantities and you want to generate other quantities using it. And there are times when you do not even want to do it on specific discretized points. You just want, when you're initializing, for example, if you've initialized your domain with an ambient pressure value and an ambient temperature value, density, and you just want to fill the rest of the variables, you just want the value. You do not want that value at a specific point. Then there are times when you're operating in the AMR mode, you did a guard self-fill, which happened because of interpolation. Now, if you really want to maintain your conservation of various physical quantities, you don't just want to use the interpolated quantities for all of the variables. You want to interpolate some of the quantities, and the rest of them you want to generate using the equation of state so that they're thermodynamically consistent and you have not lost the conservation, violated your conservation laws, right? So there are times all of these things the equation of state has to cater to. In addition to that, various different implementations have their own level of complexity. On the one extreme, you have the ideal gas equation of state, which is just a simple algebraic equation. Then you have the equation of state for the white dwarf degenerate matter, which you start out by looking through a table and then iterating, doing the Newton-Raphson iterations upon that table. And then you have the equations of state that come from really complex tables that are used in laser experiments, and you really need to be able to accommodate all of that. Then again, when you're dealing with anything more complex than an ideal gas equation of state, what happens is there are a lot of computations that are reusable from point to point. And if you really do it in a form where you're going from one point to another, you're not making use of your spatial proximity and reuse of cache very much. So you want to be able to vectorize them also. So you have all of this in front of you, for which you have to devise an interface that doesn't intimidate a person just as soon as they look at it. Present, this is the solution we have, and you go and talk to people in Flash, they'll tell you this is no good, we need to do it again. But here goes. And this was the most contentious design that happened even in the first iteration of the Flash 3. So what we do is, never mind, it's the next slide. So what we do is, what we did was we decided to have a hierarchy of the complexity of interfaces. The first thing we did was we said the one interface has to be that you provide your input quantities and you get your output quantities straight away as arguments. And that interface is there. And under that, all of the computational complexity of that equation of state can be hidden. Then, but that gets really irritating when you have to, for example, run the equation of state only on the halo, because then every time you're calling, you have to orchestrate either you have to put loops that supply the indices appropriately, etc., etc. So then we provided a wrapper function where you can give the range of indices and pass the control on to that. That wrapper function then figures out which are the points on which the individual equation of state is to be applied. The wrapper function also gives you the flexibility of then having under the hood a vectorized implementation of that single point equation of state. Then there are times when you want the derivative quantities, but there are times when you do not want the derivative quantities. So, and the argument, if you want to provide each one of them individually, the argument list gets really long. So in the wrappers, then we provided vectors which could be filled with which has indices, defined indices, which could be filled with the quantities that you want to send in as an input and then you want to get as an output, and a mask which tells you which of the derivative quantities are required and which are not necessary. And the last thing that we did was we abstracted out the knowledge of which data structure you're applying the equation of state to, because you might want to do it on cell-centered data or a face-centered data or an edge-centered data or none of those data, and you just want to provide a vector and you want to get an answer. So that's what we think provides some semblance of control in this very difficult process where a casual user comes along, they can just use the wrapped interfaces and not worry about the details. If a more sophisticated user comes along, they can use these lower level interfaces and orchestrate their own wrappers and deal with their own machinery of mass. So what it does is it gives a graded access to the capabilities provided by the equation state unit to the user. And then here, this is my last slide. This is the example of functional components in multiple units. So we have particles and grid that need to interact with one another. So the way a typical Flash run will work is the driver will run a grid init, then it will want to do a particles initialization. In particles initialization, because particles don't sit at the cell center of a cell, there is a need to interpolate the value of the variable from the cell center to the location of the particle. You need an interpolation, which we call mapping in Flash terminology. So there is a particle calls map because particles unit owns the your mapping functions, right? But then these mapping functions need to know the details of the mesh. So the mapping function in turn call grid map particles subunit that exists within grid particles subunit. Once that is done, the driver moves from initialization to the evolve state, and it calls particles evolve, which is where the time integration is going on. But then with the time integration, the particles move off their current block, in which case, evolve first wants to update the velocities from the cell centers again to the location of the particle. So there is a map which calls the mapping function within the grid. Then it does the time integration, which then calls grid move particles, which is after the time integration is done, and grid move particles makes sure that the particles get to the right block, and that was the end of it, I guess. So this is how the transfer, instead of trying to do these various functionalities within the same unit, what we've done is we've split functionality and we do the transfer back and forth in order to ensure that the correct operations happen. Questions? Because next is presentation from Sean, which will tell you how these features in Flash allowed him to build his capabilities on top.
Thank you, Anshu.
Sure.